Great. So it's a great pleasure today to have Hong Liu from IBS Korea, right? It's IBS, right?
Yes.
Oh, right, yeah. And he will tell us really interesting result about exponential decay of intersectional volume and application to various subjects. So please, Hong. And by the way, sorry, I monitoring the chat. So if you want to ask question, you can either mute yourself and ask question, or maybe if you write it in chat, then I will read it for you, Hong, so that you don't need to follow the chat. Please.
Okay. Thanks. Yeah. Thanks, Benny. It's my pleasure to be here, sharing some recent work. I suppose we have a diverse audience here, so I will do things slowly. This is mostly based on joint work with Jaehoon Kim from KAIST and Tuan Tran from USTC in China. So let's start with some basic, part one will be geometry 101, some basic fact about convex geometry. So the point I want to stress here is that in high dimension, Euclidean space, things tends to be unintuitive, not the usual one that we have, that the three-dimensional Euclidean space that we live in. So what do I mean by that? Let's start by considering two identical balls, let's say unit volume, in R3, just in the space we live in. And we know that you can, as long as you place these two balls so that they're centered, so we have this green one and black one, when their centers is close enough for some absolute constant epsilon, then the overlap, which is highlighted here, will be more than 99% of the original ball. That's very intuitive. But what happens when we move on to higher dimension? Let's take this very same epsilon that in 3 dimension we have more than 99% overlap. Take the same epsilon, then we can find you an n0 depending only on this epsilon, such that if we consider every sufficiently large dimension and look at in the high dimension Rn, I want to prove you that now if we take two same situation, a black ball centered at this black dot and a green one centered at the green dot, let's say unit volume, then you look at the intersection volume, it will be less than 1% when the dimension is large. So since the proof is very pretty, let's take a look at this proof. Basically, we just need to recall so this volume, this denotes in Rn, the volume of the ball of radius r. This is asymptotically some factor here, which you don't have to care because they are common factors. What we need to pay attention is this r to the n, exponential in the radius r. How do we then prove that the intersection volume is less than 1%? The crucial observation here is that if you look at these two balls, and if we take a center point, if you link these two centers, and you take the central point, which I use the red one, then I can draw another ball of radius r prime to enclose this intersection part. And it's high school geometry to show that when these two are epsilon apart, this r prime is bounded away from r by some additive factor linear in epsilon, additive term. Then all we need to do is to compare. So if you compare the volume of r prime, the red one with the original one, that gives the upper bound on the ratio of the intersection volume with the original one. And cancel out this common term, we have exponential decay. So when the factor is large enough, we have a very small overlap. Very pretty proof, very nice. But there is some problem here. So what is the problem with this proof? It's very nice proof, but this proof fails at the discrete setting. So what do I mean by that? Let me give you an example to illustrate what I mean here with this strategy. Let's now consider the so-called binary Hamming space. This is a discrete metric space where the ground sets are length n binary strings, and we endowed it with with Hamming metric. Hamming metric is basically the number of positions where they differ. So here they differ at the first two positions. The Hamming distance is 2. Let's consider this specific example. Take two integers, 2k, so that 2k, k and r, so that 2k is the most r. Now I take this black ball centered at this point A, and the green ball, capital B, centered at point B, where I take A and B. A is the origin. I will write it as 0 to the n to indicate the origin. B, I will write 1 to the 2k, 0 to the n minus 2k means the first 2k position is 1 and the rest is 0. By symmetry, let's try to do the same thing as what we did in the continuous setting, right? Let's try to enclose the intersection of these two discrete balls by a ball of smaller radius. But we will see that we're going to fail. So by symmetry, we may assume that the midpoint that you take looks something like C. That's the first k digit is 1, the remaining is 0. So this guy is exactly in the middle of these two, A and B. Now let's consider this purple point X. So what is the purple point X? We have the first k digit 0, followed by r digits of 1, and the remaining 0. It's easy to compute that the Hamming distance from X to both centers A and B is r. What it means is that X lies exactly at the shell of these two balls. So X lives in the intersection. But if you look at the distance between X and C, the distance is r plus k, which is even larger than the original radius. So what it means is that in this discrete setting, things are not so smooth anymore as in the continuous one. It's impossible, it's not always possible in a discrete metric space to enclose the intersection of two identical balls by another discrete ball of smaller radius. Okay. So let's leave this problem aside and come to the second part, some basic coding theory. So in coding theory, this is a small example to illustrate. So basically, we want to send messages, and sometimes we have this noise, and we want to encode the messages by binary strings to So Alice and Bob, they want to communicate, right? And Bob asked Alice a question, so Alice want to answer, and want to answer yes or no. We want to use a binary string to indicate yes and no. But if suppose during the transmission, we know that because of the noise, up to 2 bits will get flipped. And so in this very easy example, Bob received this string 0, 1, 1, 1, 0, 0. And what we have to do to tell what Alice is really saying is to just compute the distance of the received string with whatever we pre-agreed how we encode the message, right? We will compute that the Hamming distance 2 from yes and Hamming distance 3 from no. Then because we know beforehand the noise can only corrupt up to 2 bits, we know that what Alice is really saying is yes. So in general, how information theorists they deal with these corruptions during this transmission is to encode the code words. So here is our in high dimension, right? We have all these length 1 binary strings that we can use. We want to use those that I use this red cross to represent our messages, which are these so-called code words. The idea is that as long as they are pairwise far apart, let's say they are of distance strictly bigger than d, then we can always correct up to d over 2 bits of noise. All we need to do is to find the code words. Whenever we receive one, let's say here, we just need to find near which ball we lie in this of radius d over 2. And one of the central problem here in coding theory is that now I'm going to talk about a specific, okay, let's define first this A and D. So one of the central problem is to determine how many messages we can send as a function of n, the dimension. So what is A and D? A and D is the maximum number of cowords, this kind of red crosses that we can choose, the binary string, so that they are pairwise of distance at least d apart. Okay. So for the bound of A and D, there's a very classical so-called Gilbert-Verschamer bound, which provides a lower bound on this A and D coming from the 50s. So this lower bound says that A and D plus 1, let's say pairwise, they have to be distance strictly bigger than D, is at least the total number of binary strings over the Hamming ball in n dimension of radius D. So it's easy to see that the Hamming ball in dimension n of radius D, basically, let's suppose we are by symmetry, we are the origin, we have to choose up to D places to flip the bits, right, to go out distance D. So this volume is just simply the sum of these binomial coefficients. Okay, this proof is also very nice. So let's take a look at this proof, very short. So here, so what do we want to show? We want to show this Gilbert-Verschamer bound, lower bound. The idea is, let's take a code of maximal code, this red crosses, pairwise of distance strictly bigger than D. Maximal means we cannot add more, okay? Now, what we know about this code is that if you draw, as we mentioned, if you draw this ball of radius D over 2, they are pairwise disjoint because their distance strictly bigger than D. What we're going to do now is to double the radius. Let's draw this green ball of radius D centered at these cowords. The observation now is that if you take the union of this green ball, the double radius one, you will cover the whole space of 0, 1 to the n. Because suppose not, that means we will find some purple points here, right? Outside of this green region. But what does that mean? That means this green point is of distance strictly bigger than D from all the previous chosen one. Then we could have added this purple one into our collection of this maximum size called C. Okay, contradiction to our choice of this maximality. Then we just need to do some computation. This whole space has size 2 to the n. So with number of cowords times the volume of this green ball, which is the radius D volume, must be more than the number of words, the total number of strings. So that will give you this Gilbert-Verschamer bound. One of the major open problem in error correction code is when D, this distance is linear in n, then there's exponential gap between upper and lower bound for this A and D function. Okay, so that would be a very, very gentle introduction on this, one of the problems they cared about. So let's move on to our third part. The third part, the extremal graph theory. Actually, I heard about this puzzle from Shagnitas. Shagni was a student of Benny. So this puzzle, I think it's a very nice puzzle. The puzzle says we pick n irrational numbers. You have the choice to pick n irrational numbers, x1, x2 to xn. You can pick whichever one you want. And what's your goal? Your goal is to maximize the number of so-called rational pairs. What it means is that rational pair means these two irrational numbers, they sum up to a rational one. Okay, so that's your goal. And the question is how you're going to choose these n irrational numbers to maximize the number of rational pairs. So if you get bored during my talk, the students here, you can think about this puzzle. So one of the original classical topic in extremal graph theory is this so-called Turan problem. In a nutshell, I can just explain it. I'm not going to write down the precise definition. Basically, in Turan problem, what we cared about is we're going to fix our ground graph n, G, on n vertices. You think of n as a huge number, and we want to maximize the number of edges among all m vertex graph with the property that it does not contain a fixed graph H as a subgraph. And what do you mean not having H as a subgraph just means that you cannot embed a graph into another one, the injective map from the vertex from one to another, preserving the adjacencies. Okay, so one of the starting points of this Turan type problem is this classical result of Mantel, more than a century ago now, which says that if our forbidden graph is the complete graph on 3 vertices, the pairwise adjacent, if you forbid this triangle, then you can have at most n squared over 4 edges. We cannot get this bound as best possible because there are triangle-free graphs realizing n squared over 4 edges. Suppose for a moment n is even. So what we're going to do is we're going to partition the vertex into 2 equal parts, and you put all the edges in between and leave each side independent. So this bound is best possible. And I want to say that, yeah, the puzzle that I gave earlier, basically Mantel's theorem provides the answer. And the answer is the maximum number of rational pairs is n squared over 4. So the strategy is we want to think of these numbers as the vertices of your graph, okay? And you want to choose one side numbers of the form Si, some natural number plus √2, okay? And the other side is another sequence of natural number Tj minus √2. So they are all irrational, but the cross sums are rational. This is best possible just by observing that if you build an auxiliary graph where the vertices are irrational numbers and you put an edge if they are a rational pair, it's triangle free. After Mantel, Turan made a huge advancement of studying this problem where instead of forbidden 3 vertex complete graph, you forbid a larger clique, say KR. This is a complete graph on all vertices, or at least 3. Okay. For the purpose of this talk, I'm going to mention a weaker version of Turan's theorem in the complements. So for this, let me briefly recall a definition called the independence number. So what is the independence set? It's just a set of vertices in the graph on which you don't see any edge, right? So in this picture, these 3 vertices, if you just look at the graph induced on these 3 vertices, it's empty. And the independence number, we will use alpha of G to denote the size of the largest independent set in this graph G. Turan's theorem, if we rephrase it in the complement and also in the slightly easier setting of the regular graph, what it really says is that for every m vertex graph, you have m vertices. And if you are D-regular, meaning that every vertex has degree D neighbors, then you can always find the independent set of size at least n over D plus 1. Okay. Well, when we see these results, perhaps people not in this area will wonder, how good is this bound n over D plus 1? The answer is you cannot improve it, simply because we can consider G, our graph here, to be the disjoint union of cliques of size D plus 1. This is clearly the irregular. And if you choose the independent set, you have to choose, you cannot choose 2 vertices from each clique. So it's n over D plus 1. So you might say, okay, this graph is too structured. It has this, the edges cluster into these cliques. If we are not so structured, can you improve? Can you find a larger independent set? And the answer is yes. That's a very important result back in the 80s by Aitai, Komlosh, and Semeredy. So if you look at this tight example, in particular, it has any fixed size clique, right? Let's suppose for a moment, what if we forbid triangle? So first, they show that if your graph is triangle-free and n vertex and d regular, you can improve this independence number by a log d factor. They later relax this condition of being triangle-free. So how they relax it is, one way of thinking is the number of triangles, there are not so many triangles, instead of for not allowing triangles at all. And another way of seeing this not so many triangles condition is the triangles basically are the edges inside the neighborhood of a vertex, right? So another way of saying that there are not so many triangles is that if you look at every vertex, you look at their neighborhoods, N of B, there are not so many edges here. It's very sparse in N of B. So they show that if you are locally sparse in this sense, that in the neighborhoods it's very sparse, we can stick in this log d factor improvement. Okay. So far we've mentioned some basic things in three different topics, these geometric problems of the intersection volume, how much it decay as the dimension grows, and about this Gilbert-Rashomon lower bound on the error correction codes, the larger size you can take, and also on this independence number of a graph, how large independence that you can guarantee in an n vertex d regular graph. So why these three seemingly unrelated? So let's try to make some connections. First of all, let's look at 2 and 3. So I want to show you that the Turan theorem that we've just seen in the complement form implies this Gilbert-Rashomon bound that we just proved. It's very simple. So here is the proof. So all we need to do, so here, if we have an n vertex graph that's d regular, you can find independent set of this size, right? That's Turan theorem. To prove this Gilbert-Rashomon bound, basically we just build an auxiliary graph where the vertex sets of the auxiliary graph is this all the vertices are all the length n binary strings. We put an edge between two strings if and only if their Hamming distance is at most d. Now the crucial observation is that if you look at the independent set here, it basically corresponds to some strings that are pairwise distance strictly bigger than d by construction. What it means is that there is a one-to-one correspondence between codes with minimum distance more than d and independent sets in this auxiliary graph G. Okay, so what it means is that to obtain such a Gilbert-Rashomon type lower bound, we just need to give a lower bound on the independence number of this auxiliary graph. And it's not hard to see that number of vertices 2 to the n, which is exactly this guy, and the degree, this is capital D regular because every vertex is adjacent to everything within this Hamming ball of radius d, minus 1 because you have to minus the center yourself. And if you plus this one back, this recovers exactly the Gilbert-Rashomon bound. Very nice. So we've seen that how these two comes together. Then here's the why we bother to mention this geometric thing. So how does the intersection volume kick in? So recall that in the third part, this Turan type problem, we mentioned that it's possible to improve Turan's theorem by a factor of log d if we know the graph is locally sparse. And the idea is that this decay of the intersection volume of two identical balls corresponds to exactly this locally sparseness condition in our auxiliary graph. So let's just recall, what did we do when we derived the Gilbert-Rashomon bound? We define this auxiliary graph where the vertexes are the binary strings of length n, and the neighborhood of a vertex x right? Nx is the ball of center the x with radius d, right? Now, what do I mean the neighborhood of x is sparse? That means when you pick a typical point y in the neighborhood, which is inside the ball of radius d around x, y has low degree inside the neighborhood of the x. But what is the co-degree of x and y? That means that's exactly, if you think a little bit, the intersection volume of these two balls of the same radius d, center at x and y. So if we know that in this discrete setting, the intersection volume versus the ratio of these versus the original ball decays very fast, we know that in the auxiliary graph, the graph is locally sparse. This is how things comes together. So now you can forget about basically all previously what I have mentioned. Let's just focus on this geometry problem now. Let's forget about all these three parts. So our goal now is to try to give a log factor improvement on this Gilbert-Wassermann type bounds. And that boils down, what we just said, boils down to prove some decay, exponential decay on this intersection volume. Okay. And before I mention how we're going to go about doing it, let me remark that, in fact, in the binary case, even in the quinary case, Hamming space, this decay on intersection volume was known already before. So this there are several group of people, but the proof is quite heavy, computationally heavy, because if you write out, we can actually write exactly what is this in terms of like binomial coefficients. And these binomial coefficients, you can write it explicitly, but it's very hard to estimate. So it takes some considerable effort to prove such results. So now we want to take a different approach. So we don't want to compute things, which we want to bound the intersection volume probabilistically. Here's a very easy way to interpret things in a probabilistic way. So our goal, once again, we have these two identical balls, the black one and the green one. And we want to look at this shaded intersection area. We want to show that this intersection area, the volume versus the original volume, it decays something like this, where exponentially in K, where K is the distance between the center of these two balls. Okay. This is our goal. So how do we phrase this in a probabilistic way? It's actually very easy. We can phrase it as in the following way. We're going to sample a point X uniformly at random from one of these balls, let's say A. Right? This is my notation of sampling things uniformly from A. Then the probability that X lies in A intercept B in the intersection is precisely the ratio of the intersection versus the original ball. So to prove such an exponential decay in terms of the distance between the center boils down to prove when we sample X uniformly at random, an upper bound on the probability that X lies in the intersection. And we're going to do it using some sort of concentration measure. Okay, so let's try to do it. So basically, in the next slide, I'm going to describe our results in the informal way. Basically, our main result is in this discrete metric space. We cannot use a smaller radius ball to enclose the intersection. In our main result, we provide three natural sufficient conditions on the discrete metric space. And once you satisfy these three natural conditions, we can conclude that a bound that looks like this. And then what we do is we just need to, whenever we have some discrete space, we just need to verify the three conditions. And that turns out to be true for all previous studied models. Okay, so what are these three natural sufficient conditions? The first condition is some sort of growth condition. What do I mean by that? So the growth condition, roughly speaking, is that if you look at a ball inside this discrete metric space, then most of the mass is actually at the boundary. That's what we mean by growth. If you grow it, it gets heavier and heavy. All the mass is on the shell. And the point of this is that, intuitively speaking, when we uniformly random sample this X in this ball A, since we know most of the mass is on the boundary, we can kind of pretend that we are actually uniformly random sample X on the shell of the points that of distance exactly are from the center A. Okay, so we can do this conditioning. This is why we need the first condition. And this condition is very natural. If you think about Euclidean space, we've seen the asymptotic formula, that's the case. If you think about also the this binary Hamming space, we've listed this ball of radius R is of this size, right? And most of the volume is also at the boundary. So that's very natural condition. The second condition is some sort of well spread, some sort of smoothness. Very roughly speaking, is that if you look at this discrete metric space, you don't have some part that's particularly dense, has lots of points, and you don't have some part that's particularly sparse, there's not so many points. So what do I mean by that? In particular, we mean that if you look at the conditional expectation, so now let me just forget about this condition. This conditioning means that we can pretend that X is sampled uniformly on the shell. So let's just get rid of this for a moment. Just sample X uniformly at random on the boundary of A. This well-spreadness condition says, if you look at this random variable, which is the Hamming distance of this randomly sampled point X on the shell A, distance between this random point to B, to the center of the other ball, this random variable. The well-spreadness condition says we want to require that the expectation of this random variable is bounded away from the radius R by a additive term that's linear in K, which is the distance between A and B. Why this is intuitive? Let's again go back to the continuous setting. Let's look at Rn, right? In Rn, let's think a little bit for a moment. If you have these two balls, A and B, where the center is of distance K, if you uniformly random sample X on the boundary, then most of the time, X is like intuitively on this side, right? On the other side. Then this is already of distance R. And if you're on this side, you have to add something that's linear in K. So that's also very intuitive condition, okay? The third natural condition is some sort of concentrational measure on the slice. So if you look at this random variable, it's actually sort of a Lipschitz function. If you change one coordinate of X, you can only change the value by 1. What do I mean by concentration of measure on the slice? Is that if this random variable with high probability, since the expectation is bounded away from this radius R by an additive factor CK, with high probability, exponential decay in this distance K is bigger than R, strictly bigger than R. But what does it mean with high probability, the distance strictly bigger than R? That's precisely saying that X falls outside of B with very high probability. Take the complement, that means with very low probability, X lies in this intersection. And that's exactly what we want to prove. Okay. And seeing these three natural conditions, you can already sort of piece everything together to prove that, well, as long as you satisfy these three conditions, and as long as you have the corresponding concentration inequality on the slice, then we can prove the exponential decay on the intersection volume. So now, in the remaining time, let me give you an explicit example of such concentration measure on the slice. Let me take one that we proved. Let's consider a slightly different discrete metric space. Now our ground set is the symmetric group on n elements, Sn, and we endow this space again with the Hamming distance delta. So how do we see this? For each element, let's say sigma in this, right? We can view sigma as a length n vector, where each coordinate sigma I is just the image of I under sigma. So we can again view it as a length n vector. Then if you have two length n vector, you can talk about Hamming's distance again. So this is the space. Here's what we mean by a slice. Now we're going to consider a subset of permutations.
So there is another natural metric here, which you might consider by counting how many transpositions you need to go from one. But this is right. This is a kind of a more algebraic type of thing. So here you just look on them as a vectors and compare in how many coordinates they differ, right?
Right. Right. And in coding theory, they also study they study these metrics for some reason. I don't know. I'm not an expert there. So what's a slice? I use this SNK to denote the weight K slice. Weight K slice means these are the permutations where you completely scramble K points, K positions. Okay, you have n minus K fixed points, exactly n minus K fixed points. This will we mean weight K slice. Now, how does concentration on the slice look like in this setup? Here's the lemma that we proved. It looks something like this. So we have some sort of Lipschitz functions with boundary difference. So we have f that maps, that goes from this slice, K slice, to the real, such that you have this bound, whenever you take 2 from this slice, you have this bounded distance, okay? And then, given such function, what we know is that if you now uniformly random sample a permutation from the slice, we have something like a Chernoff bound, okay? The probability that it deviates from the expectation decays like this. So the proof this is not so hard. Let me just briefly mention it. You just do some coupling, okay? The idea is that how do we visualize uniform random sampling from a K slice? You can actually think of it as a two-step process. And then for each step, we're going to do a standard coupling to dominate it by a sub-Gaussian. And then you can prove it. So how do we visualize this as a two-step process? We can first choose a K set, uniformly random, that's I. That will be the set where we're going to completely scramble them. And the remaining you stay put, right? So on this set of K indices, now we just need to uniformly random sample a derangement on these K indices. So if you know this, then you can probably reconstruct the proof. Okay. Summary. Let me briefly summarize. So what I have just mentioned is the main results we have in this joint work with Jaehoon Kim and Tuan Tran. These 3 natural conditions that implies the decay on the intersection volume. So let me quickly recall these 3 conditions: the growth condition, the smoothness, the well spread of the discrete metric space, and provided also that we have concentration measure on the slice. On the slice means we are at a fixed distance from some points, right? Then we can prove this decay on the intersection volume. So so one of the motivation of proving such results is to provide a unifying framework to control such intersection volume, so that we can improve these various different Gilbert-Wassermann type bound in different settings. We look at the binary setting, but there's also quinary setting and the permutation setting that I just mentioned. Also, it sometimes works in the continuous setting. That's one application of that. And two other specific applications is there was a conjecture by Lee and Wouters about the optimality of list decoding capacity there, and basically making use of this exponential decay. So if you look at this exponential decay here, we can resolve one of their conjecture on the list decoding, the size of the list for random codes. And here it's important that for that application, you see, I didn't mention anything about K. So in our application, the distance D will be linear in n dimension. But K actually, it works for any sufficient large constant K. As long as K some constant, that's enough. We don't need K to be a function of D. So that's important for that application. And also we give improvement on very old bound on Levenstein asymptotically on constant weight code. These are the ones where you require additionally that each code word has certain weights. The number of ones in the string is fixed. That was a question asked by Jiang and Vardy in early 2000. Okay, so for this continuous setting, let me just end my talk by a small advertisement. Perhaps in the future, at some point somewhere, I will talk about it. Is another joint work is with my students Gil Fernadez and Jaehoon Kim and Oleg Pikhurko. So in a continuous setting, what we cared about is this so-called kissing number in Euclidean space. So what exactly is kissing number? Kissing number is the maximum number of non-overlapping unit balls in D-dimensional. So KD, maximum number of non-overlapping unit balls. So they can touch each other, but with disjoint interior, such that they all simultaneously touching a given one. So here's the picture. You have this center one that we given, and the question is how many you can put so that they touch this center one, but they have this joint interior. The picture, I didn't draw it perfectly. So for K2 in the plane, the answer is 6 as drawn here. You cannot pack more. The asymptotic behavior as D grows is one of the question that people cared about, and there's an exponential gap. So the best upper bound here by Kabajansky and Levenstein from the 70s used this Delsart linear programming to prove some bound of this shape. And in terms of lower bound, recently Jensen and Hughes and Perkins, they give a linear in the dimension D, linear in D effect improvement over the previous best known bound. And what we did is to give another constant factor improvement. So this is our improved lower bound. So you might say, well, what's the big deal of a constant factor improvement? I think it has some meaning, because we realized at some point that, so the proof is by the two ingredients, we use this condition Poisson point process, which is also what they did there. And the new ingredients is to make use of rearrangement inequalities. So the point of this work is that their bound can actually be obtained by discretizing the problem. So you can actually discretize the whole thing and just use recently obtained graph theoretical results to obtain the same constant as what they achieved. But that approach will not give you any better constant because the graph theoretical result is optimal there. And here, to improve the constant, we really have to work with the spherical geometry and to do some rearrangements to obtain such an improvement. Okay. So both in the discrete and continuous setting, we illustrate that some probabilistic method can be used to.
Hong, just to understand, so this linear improvement, it's exactly roughly this log, right? So this is like which comes from some kind of this triangle thing, right? So that's like always, right? So this is a log.
Exactly.
And then
yes.
That's it.
So they do it also using this condition cross-on point process in a continuous way, basically utilizing what you just said. But
but I just understand from where linear comes. Yeah. Right.
Exactly. Okay. So I think I will end my talk here. And if you have any questions, let me know.
So great. Thank you very much. Right. So I already asked some question. Anybody else? So any questions, you can unmute yourself and just basically ask directly.
Hi.
Hi.
Could you go to the main result of the lower bound, like the page before or something?
Which part?
Like the arrow, like the final bound you get for error correction code.
Oh, so basically, we in all these results, what you get is a factor that's linear in the dimension. That's the improvement you have. And to be honest, in many such cases, such linear in the dimension result is known before. And the point of our result is that it gives a unified approach that's not computation, that's conceptually simpler, no computation needed. In all previous one, they treat each one case by case. They have to do different things to compute lots of things.
Yes. But like, is there still an exponential gap between the known upper and lower bound?
Yeah. So let's just look at the simplest case, the binary one, right? Where you require the pairwise distance to be linear in n. And here, still upper and lower bound exponentially separated.
Okay, thank you.
Maybe it was saying that, right, this linear improvement, it comes from this triangle thing. And even before people understood that it comes from the triangle, so you can reduce it to graph theory. And so one of the most famous problems in this area is a sphere packing in just d dimension, and what is the density of this thing. And then the best result which people have is the density is roughly 2 to the minus d, and then people improve it by a factor of d. But to improve it even a little bit further, right? So think like you would say, okay, you improve it by linear, what's the big deal? But improve it by d to the 1 plus epsilon, right, factor, nobody knows, right? So I think there is a really, maybe recently, I saw a paper by Akshay Venkatesh, if I'm not mistaken, who attacked this problem with a pretty heavy number theory. Exactly, that's what Hong is writing, and he improves it by extra log, and this already appears to be very hard, right? So it looks like what we were doing is like very cheap. Okay, we use this independent set in triangle free graphs, we get D, maybe we can get a bit more. But surprisingly, to get even a bit more is already not clear how, right? It's a very cool problem for people to see, right?
And
so it's not clear if combinatorics helps, right?
Right. And this log D only for a sparse sequence of dimensions. So yeah, it's not clear. And I think in his paper, he even claimed that it's not even clear whether you can do exponentially better than this lower bound.
Right,
So-
right, but the gap's still huge, right?
Mhm.
Great. So, any more questions? Okay, so if not, we can maybe stop recording.